right side, which is right here, midpoint of, what's the potential here? What's the potential here? Zero. That's zero. It's moving from there, so that's zero right there. We just proved that, right? Anywhere on this line, the potential is zero, right? So we're going from there to where?
To the top.
To the midpoint of the top. So we're going from here. So how do we approach this problem?
Well, what direction? Like what direction? Are we just going straight across?
How do we approach this problem?
Where are we going?
Straight on.
Like straight off?
You're going from here to there.
Yeah.
From here to there.
Pythagoras?
I don't want to hear any math. I want to hear the idea of how to approach this problem.
First, we have to find the distance. So we have like 1/2 s right on one side and 1/2 s on the other side. So you know it'd be the square root of 2 or something like that. I had to draw to see it. I didn't do it.
What does this mean?
It's the change of potential times the charge.
That's the change of
What does that mean?
That's the change of potential energy.
The change.
Well, that's the equation for work.
What does it mean?
That's the point charge Q and times the potential, electric potential of whatever area you're in.
Apply it to this situation.
Okay.
From there to there.
From one to the first position to the second.
Come again?
It means how much work it's going to take to move from the original position to the new one.
Very good.
Yeah.
Did you hear that? Is the amount of work it takes to move the charge from, let's put it this way, V2 from V1 to V2. Follow me? Or V initial to V final. How much work does it take to move the charge from here to there?
Depends.
It's equal to the charge itself. This is the charge itself. Charge itself, that charge that you are moving, multiplied by the potential difference between those 2 points. Now, when we did the first part of the problem, we were calculating potential difference, right?
Yeah.
We were calculating the potential difference between infinity and the point. And we said that the potential difference at infinity was what?
0.
That's why I didn't bother worrying about infinity. All I did was calculate the potential at that point, because I know that when I calculate the potential at that point, I'm actually calculating the potential difference, which is the same concept here. So I know the potential here, it's 0. So all I need now to do is calculate the potential here. If I calculate the potential here, multiply it by the charge, I'm done. That's the idea. And once you understand that, you can do the math. You can do everything now. So all you got to do now is calculate the potential at that point due to all 4 charges. How many charges do we have in the configuration?
4.
So the potential at this point is going to be due to all 4 charges. So you do it one at a time, just like we did in the first part of the problem. Are you with me?
Yeah.
You got it. Once you get it, once you get the idea in your mind, you can do any problem. I'm telling you. But you got to get it. So I need the potential here due to charge 1. Let's call that V1. All right? It's K, Q. What's this distance? Over 1/2 S. Right? Is that right? V2 is KQ over 1/2 S again. Actually, I can write this as 2K over S. 2KQ over S. So that's V1 and V2. Now I need, see now the problem comes in now. We try to find out what this R, this distance is. I'm just going to call it R. From here to there. And some of you guys try to memorize the problem from the book.
Why would I do that?
But some people try to do that.
I don't think I said it right.
Don't try to memorize the problem. Understand it. Let's call this R3 and R4.
Did you finish?
So V3 is K, negative K, because now it's a negative charge. You cannot ignore the negative, over R3. So we need to figure out what that R3 is in terms of S, okay? I'm going to leave that for a little bit later. And V4 is equal to negative KQ over R4. Now, let's see. What's this angle here? Let's see. Can we get an expression? Yep. Yes, we can. Yes, we can. Can we get an expression for R3 in terms of S?
Yes.
What is that expression?
That.
Okay, R3 is going to be a half S right here plus S square, everything square, square root, right?
Yes.
And it's going to be the same thing over here.
Mm-hmm.
So that's R3, R4. All right? So let's do the little algebra here.
You can add them, bro.
S squared over 4 plus 5S, sorry, 4S squared over 4. You see what I just did?
Mm-hmm.
You follow that? Okay? It gives me 5S squared over 4. Square root, so now I can take the square root, which is the square root of 5
Times S.
S squared over 2. That's what my R3 and R4 is.
Isn't it just a regular S?
Yeah, regular, sorry. S over 2. All right, so this right here becomes square root of 5 S over 2, square root of 5 S over 2. So now all I got to do is what? What do I have to do now? Just add them up and multiply by Q. You understand? So this is going to be 2KQ over S plus 2KQ over S. I have a minus there, minus KQ over 5S over 2 square root minus KQ square root of 5S over 2. So this is going to give us, can I erase this?
Hey, Mr. Hall?
This is S.
Mr. Hall?
Yeah?
Do they expect us to simplify as much as you are?
Yep.
Really?
Expectation.
This is 4
I agree.
minus,
Needs to do it way better.
Is that
Yeah.
I could just write this as
Except for the copy now. They'll fail and
Okay. So this is going to give me 2, 2, again, so that's going to be minus 4 KQ over square root of 5 S. I can simplify it even further. If I multiply both sides, top and bottom by the square root of multiply this over here, square root of 5, square root of 5. That's going to give me, let's see, 4 KQ, square root of 5 minus 1 over 5 square root of 5S. Okay, that's my total V. So now my work is Q times V total, which is just 4KQ, little q, square root of 5 minus 1 over square root of 5 F. Done. That's the amount of work it takes. To bring a charge in. No, not to bring it in. Move it from here to there.